This is lecture 9F on mixing problems for Calculus 2. So now let's try to set up some mixing problems with some numbers so it might be a little easier. I need to know what's coming into the tank. I have a solution of 3 kilograms per liter. It's entering the tank at 10 liters per minute. Then the rate that this substance is entering the tank is the input concentration times the input flow rate. So that's 3 kilograms per liter times 10 liters per minute. It's entering at a rate of 30 kilograms per minute. This is what's coming into the tank. This is the concentration that's coming into the tank. The amount that's coming into the tank every minute. It's 30 kilograms per minute. Alright, now let's say that there's a constant tank volume. To have a constant tank volume, that means the output rate had better equal the input rate, because you don't want any change in volume here. Okay, so if the volume in the tank is constant, it just equals whatever you started with. We'll let the initial concentration in the tank be 2,000 liters. And here's the rate that the substance is leaving the tank. C out equals the output flow rate, which we said was 10, right, times Y, the substance the amount of substance in the tank, which is changing, okay, divided by the volume of 2,000. So if I carry that out, you see the liters are gone, and again I have kilograms per minute. I'm going to equate these or subtract them, so they better be in the same units. Now here's my differential equation. Oh, I need the pen. Okay, the rate that of change of the amount of the substance Y in the tank equals what's coming in. So here's coming in at 30. All these units are milligrams per something. Oh, they were kilograms per minute. Okay, so this is kilograms per minute. The input minus the output. Alright, and the output includes a Y. That's why you have this differential equation here. It's not just an integration problem, and it's a linear, it's autonomous because there's no t in it. It's first order ordinary differential equation, and it is separable. We could also solve it using an integrating factor. I want to go ahead and set up the other case, the case in which the volume is not constant, just to show you how to do it, and then we'll go back and solve them. Okay, let's say that the input flow rate is 10, but the output flow rate is only minus 2. In that case, you're going to be adding 2 liters every minute to the tank volume. You started with 2,000, but every minute you get 2 more liters because your output and input flow rates are not equal. Right. So now let's look at what we have here. It'd be the same thing. Your input concentration was 30. Remember that, kilograms per minute. The output was the substance Y in kilograms divided by the volume in liters. All right. That's 2,000 plus 2t. And here's the liters. The liters cancel, and you see I get kilograms per minute all over the place, which is what I want. Here's my differential equation. dy by dt equals 3 should be 30, minus 8y over 2,000 plus 2t. This is linear. It's first order. It's an ordinary differential equation, but it is not autonomous because the independent variable t appears explicitly right down here. So we can solve it by an integrating factor, but it is not separable, actually. Okay. Okay, once we solve these equations, we will have the amount in the tank, right? If you want the concentration in the tank, you just divide by the volume of the tank, and that will give you your concentration, which would probably be very good to know. And if you're talking about some pollutant, often it's specified in so many parts per million, so you do want its concentration rather than the total amount. Also, we might need to evaluate the constant of integration, and to do that we often use the amount of substance that was initially in the tank. So if you had the concentration in the tank and you divided by let's see, wait a minute. What am I doing? The concentration in the tank, and you multiply by the volume, you'll get the amount that you had initially. These were your initial values. The volume at time 0.